We'll proceed in vector and energy calculus. Vector and commercial calculus. Vector and energy calculus. Vector, you are amazing, you are awesome because you add direction to any computation. Adding direction to any computation is considered as exemplary because now you have everything. If someone is saying that I am walking at 5 kilometers per hour, then after 1 hour, then one person is coming and he is saying I am walking at 2 kilometers per hour. Then third person is coming, I am also walking at 3 kilometers per hour. Now if quantity is growing, then someone would ask where to where. Okay, three people, they you are walking at some speed, where to where? Okay, if I say in an atom, electron is moving. In an atom, electron is moving. People would think that okay, there is some atom inside a material, there is some atom inside that something is moving like this. Now, if someone says there are 100 electrons, they are moving, then certainly someone would ask, what is your direction? Because anyone would feel they should not collide each other. So one moment in life you need direction. If you keep going, you will hit a reason where you would start asking for the direction. Anyway, we are into the calculation of kind of energy. That's why it is commercial calculus. When we go for the energy calculation, then it is commercial calculus. Okay, so what is the scenario that we have seen as far as energy calculation is concerned? When we talk about energy calculation, okay, what we are talking, constantly I am saying, repeatedly I am saying, I have a force field. I have a force field. And this force field is generating a displacement. This force field is generating a displacement. Here I have kept one magnet. Here I have kept one magnet. Because of the magnet, there is a force field like this. And this magnet is in a way that it is distracting the kind of one metal. One metal is there. Generally, magnet, they pull the metal. Consider this magnet is pushing the metal. Now this metal is kept here. This is not a circular loop. This is a closed loop. Oh, this is a closed loop. I closed it. There is a path like this. Okay. So there is a path like this. And path, now I am going to close it. Now path got closed. Okay. So when path got closed, consider, this is the example I always give. Consider one nut, iron bolt, iron bolt. I pierced it inside this, and it will rotate now along this curve only. Okay, if that is the case, it would rotate along this curve only. If this is the force field, then this metal is rotating like this. This metal is rotating like this. If this metal is rotating like this, then how much I have kept one magnet here. Secretly, I have kept one magnet here. And magnet tendency is if any metal comes into the picture, it get distracted. Or someone would say this bolt has some magnetic field in it, and when it comes in this magnetic field, then north pole, it starts getting distracted. Or there is a metal, it starts moving because of the magnetic field. If magnetic field has some energy, consider magnetic field has energy x, and because of the magnetic field, there is a force vector. Because of this force vector, this bolt is moving like this. Okay, because of this force vector, the bolt is moving like this. Now, if bolt starts from here and it starts moving and then it is moving back here, then what is the energy I see in the magnet? Magnet is losing energy because bolt is moving. Okay, consider before the bolt started moving, the magnetic energy is X, and after that, when bolt moved from here back to here, energy is again X. This proves that there is no work done. There is no work done. Okay, if I move an item in a closed loop from one point and back to another point, and it is losing energy, it is losing energy. In this sense, the magnetic field did a work. When you do a work, you lose energy, and typically you get energy through food. So if the item is moving from point A and coming back to point A, and magnet which is showing the magnetic field, it is losing energy, means there is a work done. If it is not losing energy, there is no work done. Here concept comes as path dependent and path independent. If the magnetic field force vector is path independent, it does not depend upon the path the item is moving. It only depends upon the begin path and end path. If begin part and end part is same because it is moving from here and coming back to here. If begin path and end path is same, then it is considered begin path and end part is same, and energy lost by the magnet or the work done by the magnetic field is zero. Is work done by magnetic field is zero when item is moving from A to somewhere and coming back to A again. Then it is called path independent because work done is dependent upon the begin point and end point. Begin point is A and end point is A. No work done. If there is work done, if item is moving from point A back to point A, if there is a work done, then it is not path independent. Okay? Because A to A, if I do any integration, it should be zero, but it is not zero. So now we are in situation that first how to identify a vector force field is path dependent or path independent. Okay, in that scenario, if through any path, if I calculate the energy computation through any path, if I can calculate energy calculation from point A to point A, from point A to point A through any path, if I calculate closed path, if I calculate energy calculation and it comes to some quantity, then it is path dependent. Okay, if it is zero, it is a candidate for path independent, not certain. If I take point A and coming back to point A, there is a path that is traced. If same point A to point A, if I take another path, some zigzag path and coming back to A, not guaranteed that in every closed path from point A to A, it will be zero. In some paths it may be zero, in some paths it may not be zero. But if it is not zero, then certainly it is not path independent, it is path dependent. If it is zero, then it is a candidate for path independent. Okay, what is the hard and fast rule to know that a force field is path independent? Okay, the net energy calculation as we have described it, the net energy calculation for the force field capital F is capital F dot D of position vector. If I don't go with the calculus, D is not there, then capital F force field dot displacement vector. Force vector dot displacement vector talks about the energy computation, work done. But if it is algebra, then we go with integration. Force field dot D of position vector. If I do differentiation of position vector, it comes as another vector, that is the displacement vector. Why you are talking like that? You can place directly displacement vector. In some cases, in curve kind of situation, displacement vector is variable. If this is force vector, first of all, force vector can also be variable. Force vector is like force vector is like Earth gravitational pull. Consider this is Earth. This is Earth. This is cross section of Earth. So I'm going to get a better earth. Okay, consider this is earth. Okay, I believe, oh, this is very heavy. Consider this is earth. This is really earth. Okay, it looks like not a sphere. Consider it is a sphere. Now, what about the earth gravitational pull? Earth gravitational pull. Okay, now if I see this direction, the earth gravitational pull is along this direction. If I see, then direction change, right? It should be constant. If I take vector, all vector, all vector in parallel to each other are considered as same vector. But here, the earth gravitational pull here is different. Earth gravitational pull here, it is different. See the direction. Here it is different. Here it is different. Here it is different. All are radial to the earth. One thing. Second thing is gravitational pull. Gravitational pull is different. When someone is near to the surface, the pull is very high. But if you go far, 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 the pull is slow, less. The gravitational pull force is less. If someone goes 100 kilometers from Earth, then potentially he will not fall on the Earth at all. He will enter into space where he will start floating. So that is the means if you go distance wise, then force is different. If you go direction wise, the coordinate, if you change the XYZ coordinate, again force is different. Okay, in that sense, Earth gravitational pull is algebraic. What is the algebra of the Earth gravitational pull? Minus gm. G is some constant. M is mass of the Earth. R vector. The vector, I hope it is very heavy. Very, very heavy. I believe some 4 kilogram. Good. It is very heavy. Okay. So if kind of if there is a vector like this, if there is a vector like this, or I believe it's all right, understandable. So if vector, oh, I can get it. Oh. Okay, there is now one item. Okay, there is one item, and this item is this item is revolving around the earth. Now, if it is revolving around the earth, every position it is different. It is attracted like this, it is attracted like this, it is attracted like this. So the direction of gravitational pull is different. One thing. Second thing is that if it goes far, then power of the gravitational force is different. What is the equation? Minus gm r vector by r to the power 3. That is the equation of gravitational pull. Okay. So g is constant, m is mass of the earth, r is the r vector. This is r vector. R vector means the radial vector. R vector means radial vector. This is R vector. This is R vector. This is R vector. This is R vector. Everywhere R vector is. This is the R vector in polar coordinate system. If this is the R, if this is the R vector, then the gravitational pull is minus gm R vector divided by R to the power 3. Now tell me, this is path independent or not? That is the question. So for path independent, the energy computation is force field dot d of position vector. If I take any point in the space that is x comma y comma z, then the position vector here is xi plus yj plus zk. Xi plus yj plus zk. Force vector capital F vector, capital F vector is minus gm r vector divided by r to the power 3. R vector I can consider at xi plus yj plus zk. If that is the case, then it becomes minus gm xi yj zk plus plus. divided by x square plus y square plus z square to the power 3 by 2. This is the force field. So force field capital F can be represented as F1I plus F2J plus F3K. F1 is minus gmx by the magnitude x square plus y square plus z square to the power 3 by 2. F2 is minus g1y by x square y square, and F3 is minus gmz by x square y square, whatever it is. Now if this is the case, then this is the work done. So as we have talked, so our net energy calculation is F1 dx, F dot d of position vector. D of position vector is xi plus yj plus zk. If this is at any point, if this is x comma y comma z, the position vector from here is xi plus yj plus zk. F dot d of xi plus yj plus zk. F is f1i plus f2j plus f3k. Dot d of xi plus yj plus zk. F1 dx plus f2 dy plus f3 dz. That is the net energy calculation. Consider it comes as an algebra, and that is g of x, y, z. If dg by dx is f1, if dg by dy is f2, if dg by dz is f3, then g, the net energy calculation, is dependent only upon f1, f2, f3 on force field, not on the direction, and then limit, lower limit to higher limit, not on the direction, only begin limit, end limit, and on the force field. If any energy calculation is dependent only upon the force vector field and the lower limit and higher limit, means begin point and end point, then it is path independent. Let's consider the earth case. Earth case, now it will be F1, that is minus G1 G minus Gmx by x square plus y square plus z square to the power 3 by 2 dx, minus Gm y by x square plus y square plus z square to the power 3 by 2 dy, plus minus Gm z by x square plus y square plus z square by 3 by 2 dz. That is the net energy calculation. How much it will come? How much it will come? Okay. Now, in other way, people also say, can you find one algebraic equation G for which partial derivatives are f1, f2, f3? If you are able to do it, then it is path independent. Okay, consider I have an algebraic equation that is, I have an algebraic equation that is 1 by 2 log of x square plus y square plus z square. Okay, log of x square plus y square plus z square. Okay, I don't know, miss, this is what I am thinking. Okay, is it the right one? I don't know. Or let's say I have algebraic equation 1 by, I don't know, I'm just speculating. Consider I have algebraic equation x square plus y square plus z square to the power minus 1 by 2. X square plus y square plus z square to the power minus 1 by 2. What is its partial derivative with x? Then d of x square plus y square plus z square to the power minus 1 by t of dx. First differentiate it with x square plus y square plus z square. If I differentiate it like this, then it will become 1 x square plus y square plus z square to the power minus 3 by 2. Minus, I'm sorry, okay, if it is minus 1 integration, if I integrate, then okay, I have to kind of, I really don't know what is the answer to this problem. Okay, oh sorry, I am differentiating it, not integrating it. Nice. X square plus y square plus z square to the power minus 1 by 2. Now it's all right. If I differentiate with x square plus y square plus z square first, and then d of x square plus y square plus z square by dx as per the chain rule. Now it will become x square plus y square plus z square minus 3 by 2. Differentiation of x square plus y square plus z square to the power minus 1 by 2 by d of x square plus y square plus z square will become minus 1 by 2 into x square plus y square plus z square to the power minus 3 by 2. And this side 2x, 2 gone, 2 gone, minus it will remain. So if I have a function called minus 1 by x square plus y square plus z square to the power 1 by 2, the first partial derivative along x-axis would become x by x square plus y square plus z square to the power 3 by 2. This is what we want, right? Another one is d, somehow I found it. Another one is the d of, another one is I have now potential function g is minus 1 by square root of x square plus y square plus z square. That of d of dy. Again, it will come as y by x square plus y square plus z 3 by 2. It is exactly what we want. Only difference is minus minus something someone has to settle down and gm someone has to add. Means there is a potential function that exists for which partial derivative is the earth gravitational force. Means earth gravitational force is path independent. This proves earth gravitational force is path independent. Means your force vector field is radial. If force vector field is radial, then it is path independent. If it is not radial, then probably it is candidate for path dependent. If it is path dependent, then in a closed loop, like here, if I say my satellite is moving from here, it is moving from here, and then it is moving from here, and it is making a round of the earth. From here back to here, how much is the energy that lost by the earth because of the satellite? If satellite is dropping on the earth, then it is because of the earth only. Earth is attracting it. This is not the mathematics terminology, this is physics terminology. Earth attracts anyone, as per Mr. Newton. Okay, but with mathematics, Earth is working because it is displacing something from here to here. If Earth is working, then how? Then it is losing energy. So if something is coming towards Earth, oh, it is very heavy. If something is coming toward the Earth, then Earth is losing energy in that fashion. Okay, but if something is revolving around the earth in a circular fashion and earth gravitational pull is radial at every moment, then earth is not working in that fashion. Okay, or okay, you talked about radial. What about this? If something is coming from here to here and coming back to here, again, then what is work done? No work done. From point A to point A, there is no work done because kind of Earth is kind of path independent. But if you move in circular direction from this point to this point, also there is no work done. If you move along the Earth along the radius, then certainly there is work done. But if you go back to same location somehow, then there is no Earth gains energy. But if you move in radius direction in along the arc circular direction, then Earth will not lose energy because Earth gravitational force and this displacement direction both are 90-degree to each other. If that is the case, then Earth will not lose any energy if you go from point A to B. No need you complete a circle. That's why satellites they rotate in a circular fashion so that Earth gravitational pull will have no impact on them because it is perpendicular. But if you move around the Earth and come back to the same location somehow, then Earth won't lose energy. First it loses energy, then it regains the energy. Okay, that is the path independence fundamental. Okay, if it is path independent, now can I try one equation? Now xi plus yj, there is a function called xi plus yj, force field xi plus yj. What is the scenario of xi plus yj? Okay, xi plus yj. Now if I take xi plus yj, if I take, then from here to here, if I see the x-axis, then it is along the x direction, xi plus yj. Here y is 0. On x-axis, y is 0. Xi plus yj is the force field. Then y is 0, then it is along the x-axis. Okay, xi plus yj along y direction, where x is 0. Where x is 0, then the force field is along j direction. Here force field is along, it looks like if it is 1 comma 1, then in I plus j in this direction. This is again radial. Xi plus yj is again radial. What about minus yi plus xj? Minus yi plus xj. If that is the case, then if I take any point on x-axis, it is xj, y is 0. Then it is along this direction. If I go in y-axis, then it is minus yi plus xj. X is 0. Minus yi. Minus yi means along this direction. This direction here, this direction here, this direction here. Looks like this is anti-clockwise. This is anti-clockwise. Or if I take yi plus xj, then it is clockwise. I'm sorry, yi plus xj. I would say yi minus x minus yi minus xj. Yi minus xj. Then here on the y-axis it will be like this, yi minus xj. Here it will be down. So it will be now clockwise direction. The force field is yi minus xj. Yi minus xj. Now, okay, so let's proceed. Now, if I try to find the energy computation in a closed loop, not circular loop required. If I start from a point A and come back to point A under a force field F, how much energy is dissipated by the energy source because of which this is the force field? This kind of demonstration is not available anywhere. Just this dot, that dot, and integration, and here and there. That's it. Okay, there is an energy source through which there is a force field. An item is moving in a closed loop from one point and coming back to the same point. How much is the energy dissipation from the source field? Now the vector field, if it is path independent, then no energy is dissipated because net work done is 0. If it is path dependent, then we have to calculate the energy computation as per the F1 dx plus F2 dy. F1 dx plus F2 dy, or F1 dot dr vector. R vector is the position vector of the path, or dp vector. That is energy computation, that from point A to point A. This is what we say. Point A to point A, whatever it is, how much it will be. Point A to point A, whatever you calculate, point A to point A will be 0 only. If you integrate anything from point A to point A, certainly it will be 0 only. So generally people, they dissociate from point A to some point B plus point B to point A back. Okay, then what is the energy computation? Okay, or people use Green's theorem. Green's theorem, no, it is impossible, right? Calculating the energy that is dissipated in a closed loop, point A and coming back to point A. Okay, you can use Green's theorem. That is the, first you calculate the curl tendency of the vector field, df2 by dx minus df1 by dy. This is the curl tendency. Or in 3D it is I vector and then df3 by dy minus df2 by dz, I believe so. Okay, df3 by dy minus df2 by dz in I direction plus j direction plus k direction. Whatever it comes, calculate the magnitude of it. That is the kind of net energy calculation. Then integrate with dx, dy, dz. Let's take in 2D only. If it is 2D, we are calculating the energy calculation in a circular loop. We are calculating the energy calculation in a circular loop in 2D. Then it is dz by df2 by dx minus df1 by dy. This is what we have seen. Okay. How, what is the proof of it? If it is path independent, the way we said, if it is path independent, then the net energy calculation comes as G. G, then dG by dx is F1, dG by dy is F2. If I go further differentiation, then dG by dx and then dG and then again differentiating with dy, then it becomes df2 by df1 by dy. dg by dy is f2, dg by dy dx is df2 by dx. Now dg by dx dy and dg by dy dx both are same. So if for the path independent scenario, df2 by dx is same as df1 by dy. If it is not same, then df2 by dx minus df1 by dy, it will resolve into some algebraic equation or some numeric value. That numeric value is called torque value or curl value. Okay, like example we give, like if I take point A and point B, point A and point B, and connect it through a vertical line and then through horizontal line. This is how you connect point A and B. First through vertical and then through horizontal. If there is df1 by dy, f1 is going in this direction of the force field. If it varies along y direction, then it will not be the same all along this line. It will produce a torque. If there is df2 by dx, then it will produce a torque. Net torque produced on this line is df2 by dx minus df1 by dy. Green is saying that df2 by dx minus df1 by dy, that is the net torque. If you integrate with dx and dy, and then limit, you take the closed loop region. So if this is the closed loop region, that is elliptical in the case, whatever is the region is, integrate along that region to dx by df2 by dx minus df1 by dy, dx dy, you will get the net line integral or net work done or net energy calculation when your item is moving in an anti-clockwise direction, starts from one point and coming back to the same point, whatever it is. You can calculate this. I'm trying to find many ways to calculate the energy computation by a mass that is moving from point A and coming back to point A. One is F dot dr or F dot d position vector. This is what we are saying. Calculate the net integration and then set the limit point A to A. It is not possible, then break it, point A to B and B to A. Now calculate the net energy calculation, or df2 by dx minus df1 by dy, dx dy, integrate over the circular region. X is from here to here, y is from here to here. That also gives the energy calculation. Okay, if it is in 3D, then how it is in 3D? 3D means your circular loop is 3D means your circular loop. If you take point A and any point B, then you can make a kind of a circle. To make a point in a circle, that circular point from point A and coming back to point A is not in any of the plane. It is in xy plane, then it is 2D. If it is in xz plane, then it is 2D. Okay, if it is in yz plane, again it is 2D. But if it is in, like, if it is everywhere, then it is 3D. If it is 3D, then calculating the work done from point A back to point A when force vector field is not path independent, it is difficult. In that sense, you have to use Green's theorem only. Now, Green's theorem is saying to calculate that, you have to calculate the curl, torque factor. Torque factor is, now in 3D, it is I vector and then df3 by df3 by dy minus df2 by dz plus j, then again something df1 by dz minus df3 by dx plus k, something like that. K vector dz by df2 by dx minus df1 by dy. This is the called torque vector. Torque vector. We calculated torque right now, right? If it is consider xy plane, a point here is one point here and one point here, if there is a path, this force field would generate a torque on the path. Okay, torque on the path, because df2 by dx minus df1 by dy, they are not cancelling each other. It will generate a torque. In 3D, torque calculation is what I say. You have to take a matrix, and first row is I, j, k. Second row is gradient vector, that is d by dxi, d by dyj, d by dzk. And third is f1, f2, f3. f1, f2, f3. If you calculate this matrix, if you compute this matrix, then it will come in a vector form ijk. That is the torque vector. That much torque it would generate. Okay, integrate this with dx, dy, dz, and along the cubical region, then you get the net energy flow, net energy flow, that net energy, that is consumption happened from the energy source when it is moving in a circular region, in that region. So here it is x, y, z. That's the circular region what we are talking. It has three components: x component, then y component, then z component, all three. So generally people they do is they take in a 2D side, because one point to one point can be solved in a 2D way only. If that is the case, then it is x from lower limit to higher limit, y from lower limit to higher limit, df2 by dx minus df1 by dy, dx dy. But this will be along the k direction. If I take x and y, then it will be along k direction. Or if I take all three vectors, then it will be in some direction. Understandable, right? Because it has I, j, and k both. It will be in some direction. The torque will be in some direction. Okay. Now there is a terminology called circulation density. Circulation density. Circulation density means if my force is not path independent, consider this is path dependent. If force is path dependent, then item is moving from this point and coming back to this point again. Then how much energy is computed? Energy is forced into more or less displacement vector. If displacement is bigger, then probably energy that is dissipated by the energy source is more. If this displacement in a closed loop is very small, from this point to this point, then energy computed by the energy source is less. I don't want dependent upon the displacement. I want the energy density. This is also called circulation density. Okay, circulation density means what is the tendency of this energy source to make anything rotate. Then whatever the energy computation we are getting through a closed loop, divide by the area, or energy computation in a closed loop from A to A. I am saying, just say integration in a C means closed loop, force vector dot d of r vector or position vector. Okay, divided by area, divided by the area is the circulation density, not up to here. Because now consider that this is this area. Now this area is fixed. Area is fixed. But will it be fixed f dot dr? Because they are vector, force vector and position vector. If I change like this, then position vector is changing. If I do like this, then this is xz plane. If I go with this is xyz plane. All three. If I go like this, then this is xy plane. If I go like this, then this is xyz plane. Okay, it is changing. If this is changing, then the top, what we are seeing, the line integral, energy computation, force vector dot d of position vector will keep changing by area. Area is same. That is non-vector. Keep doing like this. Keep changing in all the direction and compute the energy calculation. Divide by the area. The position where it is maximum, the energy is maximum in whatever direction it is, that by area, that is called circulation density. Circulation density, if I divide by area, then we are making it independent of the curve length, because curve length is more, then area is more. Curve length is less, area is less. What we are getting with this? Energy computation in a closed loop divided by the area means we are trying to find the curling tendency of force field. We'll talk more on it. I believe it is too much. Okay, we are into commercial calculus. We are into energy calculus. Calculus that solves the energy kind of scenario. Okay, we'll proceed on this. This is what I think so. Circulation density, energy that is dissipated by energy source when item is moving from one point and coming back to the same point. Okay, in a circular fashion. Divide by the area that it is making, the 2D area. If I divide like that, then what is the energy density? Density in the sense that per unit area, how much is the energy? I believe this is better one. So if my area is 20 meter square, how much energy it is coming out of my energy source? If it is 1 meter square, then how much energy? This is circulation density. Per unit area, how much energy that is being dissipated. But it has many more things to compute upon. So we will talk on it. Please do support us. +91 is the India country code. 9483160610 is the telephone number. 9483160610 is the telephone number. +91 is the India country code.